like CNN, we wanted to do something similar for text and speech. But text and speech have this crazy requirement that you need to be able to memorize part of the data in order for you to be able to predict some part of the future. So you needed different architecture which was able to retain memory. So CNNs and MLPs were not efficient. So what we did is we looked at the architectures for neural networks which had cycles in them. The very notion that we can have cycle in a network allows us to store memory, and that's a huge benefit. So we saw that RNNs were a great tool in terms of being able to capture data which was sequential, where there was dependence of data in one part, which is probably earlier part of the data on later part, or it could be reverse, like a later part dictating the previous part. So in all of such scenarios, whether it is time series modeling or whether it is text sequence modeling or whether it is predicting sequence of images in a video or whether it is predicting speech syllable sequences or whether it's predicting character sequences like what you do in a swipe keyboard, name a sequential prediction problem, RNNs are there. But we also saw RNNs have a basic problem, which is basically that of, because of the partial differentiation of the errors and propagation of the errors through the network and the unfolding of the network into many replications of the same node, the net product going to zero in either vanishing model, or if it is slightly above one, it's going to infinity by exploding gradient, which causes the problem that the model may not may not converge to a stable point, which can be eliminated, which can be presented as a funnel classifier or the regression model. But the idea is you need to be able to take a look at handling this by some way of providing a more stable memory architecture. That's where we had two innovations we saw, which was LSTM and GRU. LSTM was slightly more complex in the sense that it had 4 gates. It is 3 gates and 4 different layers inside one cell. It gave it a notion of memory and not necessarily being affected by vanishing gradient. GRU was slightly more simpler, but more commonly LSTM is what is used. So unless we talk about LSTM specifically or GRU specifically, if we talk about RNN, we specifically mean LSTM as the default architecture. That's the best practice in the industry. But then what we also seen is that there are several scenarios where the sequence modeling problems may not be exactly of the type what we looked at in modeling our LSTM applications. We looked at example where we predicted a sequence in a retail sales. Then we started looking at how such a sequence could be used in, say, word prediction or character prediction. But there are several scenarios where where a sequence can be input and a sequence is predicted as output. So in such cases, it is not like we're talking about just predicting a single character as the next predictable character, or just predicting the next requirement of what we call as explicit prediction of a single output as a result of the regression model you learned with a simple LSTM. So here, the idea is you give a sequence, you get a sequence as a response. What kind of examples? I'll give a very simple example. Let us say I give a set of English sentences and I get a set of translated Telugu sentences as a response to that. So in such machine translation projects, we can model them as a sequence to sequence translation, which is a natural way of looking at it. Or I'll give you another example. Let's say we're building a chatbot and we have given utterance to a chatbot. We get the response from the chatbot as a sentence. Then in response to that chatbot utterance, we send a response back. This sequence goes on. Suppose you have n such, so suppose you have 2n such conversations. Then you will actually be able to model it as 2n minus 1 pairs of sequence to sequence, because if I speak something and the chatbot responds back, that is one sequence. If chatbot responds something and I respond back, that is another sequence to sequence. So modeling a 2n chat sequences as a 2n minus 1 sequence to sequence problem is a fairly common way of modeling chatbots. So in fact, one of the very popular ways of creating your own custom chatbots is by taking a lot of previous conversations between agents and customers and taking them and creating a sequence to sequence model. So these are some of the examples where we have one time a sequence is given and output is expected as sequence. So we wanted to mention that it is not just about a RNN or LSTM architectures about predicting simple element as a sequence, but we can predict sequence as a response to a sequence as input. Also important to note that sometimes length of the input and output may vary in terms of length. So this type of problem is typically what is known as many-to-many sequence prediction problem. So how do you capture this kind of problems in sequence modeling? This kind of modeling is typically captured by what is known as encoder decoder model. Then it becomes a question of modeling two different networks, one an encoder, another a decoder. So what happens is this follows the principle that we Indian languages are very used to. For example, if we want to translate one of the Indian languages, core Indian language to another, we have a huge advantage in having a common root in form of Sanskrit or Prakrit grammar. So what you do is you take a Telugu sentence, you can convert it into an intermediate Sanskrit grammar, and then take that grammar and convert it into the target language, like say Hindi. It's exactly the same thing model which is used in encoder decoder architecture. So what this does is it takes an encoder model, which is probably an LSTM or a GRU or an RNN, which reads the input sentence and encodes them into an intermediate fixed length vector. Then we have a second LSTM or a GRU or an RNN, which takes the fixed length vector and outputs the predicted sequence. So it is important to understand that this kind of an architecture is basically called as encoder decoder architecture. These are primarily well suited for sequence to sequence problems. So what these do is they consist of two RNN architectures. One acts as encoder, another as a decoder. Encoder maps a variable length source sequence to a fixed length vector, and the decoder maps the vector representation of the fixed length back to variable length target sequence. So what happens is such kind of model is very useful for sequence to sequence translations, not only in conventional scenarios, but also places where input sequence is reversed, or even when we have very long input sequences. In all of these kind of variations also, such kind of models have been proven to be very, very useful. So this is the way it works. You take an input model, you take a encoder model, create the fixed length vector, then take the decoder model, then output this by passing it through a dense neural network, which is fully connected network, and get the output corresponding to the output of the decoding. Fairly simple, but it's a good extension to the basic idea of the what we call as extension of the core LSTM GRU RNN architecture to a broader class of problems. What are the example applications? So an example could be, for example, it's not necessarily that both sides should be LSTM. That was the one example we gave. But here, we talked about an example which is not necessarily LSTM. We can have a combination of CNN as encoder and decoder as LSTM. So a CNN as encoder could be having images as input, and it could be read by a decoder LSTM which could feed a text as output.